In this video we're going to cover section 3.5, Implicit Differentiation. In this section there's a couple bullet points we're going to hit here. We're going to distinguish between functions that are written in implicit and explicit form, and we're going to use this implicit differentiation to find the derivative of a function. So up to this point most functions have been expressed in an explicit form. For example, in the equation y equals 3x squared minus 5, the variable y is explicitly written as a function of x. Again, explicit form is we have y all by itself here on the left, and y is equal to something, and that something is in terms of x. Some functions, however, are only implied by an equation. For instance, the function y equals 1 over x is defined implicitly by the equation x times y equals 1. Suppose you were asked to find dy dx, the derivative of y with respect to the x variable for this equation. You could begin by writing y explicitly as a function of x and then differentiating. So here's the equation we're given, x times y equals 1. That's our implicit form. To put it in explicit, we solve for y. Divide both sides by x, so y equals 1 over x, or x to the negative 1 power. And then we take the derivative. dy dx is negative x to the negative 2, and we rewrite it to get rid of that negative exponent. This strategy works whenever you can solve for the function explicitly. You cannot, however, use this procedure when you're unable to solve for y as a function of x. For instance, how would you find dy dx for this equation? And what really gets us here is we have a 2y to the third and a plus 4y. Could you solve this equation for y equals something? No, it's probably impossible, or it could be very, very difficult. To do this, we can use implicit differentiation to find that derivative. To understand how to find dy dx implicitly, you must realize that the differentiation is taking place with respect to the x variable. This means that when you differentiate terms involving x alone, we differentiate how we have been up to this point in the class, just with those power rules and chain rule. However, when you differentiate terms involving y, a different variable, we have to apply the chain rule, because you're assuming that y is defined implicitly as a differentiable function of x. So here in example 1, this hopefully will clear it up a little bit if there's any confusion left. In letter A, we are trying to find d dx, the derivative with respect to x of x to the third power. And here we see the variables agree. We're deriving with respect to x. This term only involves the x variable, so we use our simple power rule. Bring the 3 down front, 3x to 1 power lower, 3x squared. But what if the variables do not agree? This is the chain rule. So here we have d dx, we're taking the derivative again with respect to x, of a term that is y to the third. These variables do not match. So we're sort of going to do the chain rule. Imagine this is our u substitution. We're just going to let u equal the y variable. We take the derivative, it's just 3y squared. We derive that y to the third just like we would if it was an x variable. But by the chain rule, our inner function is y. So what is the derivative of y? Well, that's dy dx, the derivative of y with respect to x. So when the variables agree, just derive like we have been doing. If the variables do not agree, you're going to tack on a dy dx at the end. Let's look at letter C here. Derivative with respect to x of, now we have two terms, x plus 3y. Well, the derivative of the first term, that's in terms of x, and the derivative of x to the first is 1. And then we have plus 3y. The variables do not agree now. X and y are different, so we derive this as we would if it was x. What's the derivative of 3x? Well, that's just 3. And now by the chain rule, y is always our inner function. What is the derivative of y? dy dx. Or you could use y prime. Letter D here. Now we have x times y squared. What rule are we going to need to apply to find this derivative? Product rule. We have x times y squared. So the derivative of the first thing is 1. What is the derivative of y squared with respect to x? Well, the derivative of y squared would be 2y. And then because the variables disagreed, we add on a dy dx. So now we can do product rule. So our derivative with respect to x is going to be first times the derivative of the second, x times 2y dy dx, plus, that was first times the derivative of the second, plus second times the derivative of the first, y squared times 1. So there's our derivative d dx. That is the derivative of the function with respect to the x variable. Implicit differentiation has these, basic guidelines. 1, differentiate both sides with respect to x. Number 2, collect all the terms that have a dy dx in them on the left side of the equation, move everything else to the other side. Then when all those terms on the left side have a dy dx term, you can factor that term out of the left side of the equation, and then, divide through by whatever's left to solve and isolate dy dx. In the next example, example 2, note that implicit differentiation can produce an expression for which the derivative contains both x and y variables. And you'll see why that has to be there, so when we start looking at these graphically. So example 2, find dy dx, given that y to the third plus y squared minus 5y minus x squared equals -4. So that's a pretty nasty equation we got there, and we are going to derive that with respect to x. So the derivative of the first term, y to the third, the variables disagree, so it's going to be 3y squared, just that simple power rule, and because the variables disagree, we tack on a dy dx. Plus y squared, plus, again, y squared, the simple derivative of that would be 2y, and because we are deriving with respect to x, we create another dy dx. Minus 5y, minus, well, the derivative of 5x would be 5, and then by the chain rule again, the derivative of that inner function, dy dx. And now finally we get a term where the variables do agree. Here now it's minus x squared, minus, and because we're deriving with respect to x, and this term only involves x, we just derive it 2x. And then equal to, the derivative of any constant is 0. So back to the guidelines, we differentiated both sides. Now we're going to collect all the dy dx's on the left side and move everything else to the right. So that's an easy fix. These terms have a dy dx in them, so they're going to stay here on the left side of the equal sign. This 2x is going to move over to the other side. So I got to rewrite all this just to move, just to move that -2x over. dy dx minus 5 dy dx equals 2x. Okay, now by the guidelines, the next step is to factor this dy dx out. So since every term has it, we can have dy dx, and then what is left inside is our 3y squared plus 2y minus 5, and that is equal to 2x. And the last step, again, the end game is to isolate the dy dx. That's the derivative we are solving for. So we're going to divide both sides by what is in that set of parentheses. Our derivative of the original equation is equal to 2x all divided by this quantity, 3y squared plus 2y minus 5. And again, note here it says in example 2, implicit differentiation produces an expression for which the derivative contains both x and y variables. And why is that? If we look at this graphically, the original function here, this y to the third plus y squared, etc., etc., if we graph it, it's going to look like this shape. Now this is not a function. It fails the vertical line test. So let's just say I came here to -1.5. That's -1.5. If I plug in that x value above or below, I would hit the function at 3 possible points. I might hit it here, I might hit it right here, or down here near the bottom. So remember, we're trying to find the slope, or the instantaneous rate of change at a point. If I was looking for the slope at this point, it's going to be downhill, negative. Here it's going to be uphill, pretty steep. Down here it will also be, a slighter more subtle downhill slope. So each of these 3 points on the graph have different slopes. So if I want to find the slope at this point up here, I would have to plug in the negative 1.5 x value and the y value, whatever it is here on the y-axis to go with it, to get that actual slope or rate of change. If I wanted to plug in this point down here, I'd plug in the same negative 1.5 on the x-axis, but I'd have a different number over here on the y-axis. You know, there are x's and y's in this derivative, and that's because, you know, this technically isn't a function. It does fail that vertical line test, and there could be different points with different slopes for any given x value. Example 3, representing a graph by differentiable functions. If possible, represent y as a differentiable function of x. So let's see here. Can we just solve this for y? Well, we could move the x squared to the other side. It becomes negative. Negative x squared is a quantity, and then we would square root both sides, so we would have y equals, because we square root both sides, a plus or minus. And that's going to mean it's not differentiable. And actually, if we think about it, x squared plus y squared equals 0. What exactly would that graph look like? 2 squared terms are added together and they add up to 0. No matter what x and y are, positive or negative, if you square it, it will be positive. And if you add 2 things together and they equal 0, and both of them, or neither of them, is a negative, what does that have to be? Well, that means x and y have to be 0 themselves, and it's just a single point. It's actually the origin of the coordinate plane, and a single point is not differentiable. And let's look at letter B. Letter B is pretty close. It's x squared plus y squared equals, but now it's not equal to 0, it's equal to 1. So if you remember from pre-calc, you might have an idea what this shape would be if we graphed it. Again, let's solve for y. Get the x squared on the other side, 1 minus x squared. We would square root each side then, and we would have y equals plus or minus the square root of 1 minus x squared. And back to the original function, x squared plus y squared equals r squared is the equation of a circle. So here our r squared would be 1, and the square root of that is 1. So this is just a circle of radius 1 centered at the origin. And here's what those plus or minuses mean. The plus, we would plug in a number for x, square it, subtract it from 1, take the square root, and we would have a positive portion of that, which would be the upper half of the circle that is in positive y territory. These are positive numbers on the y-axis. The negative sign would be, we would do the same operation under the radical, square root it, but now whatever that answer is would be negative. That would be our half of the circle that is under the x-axis in negative y territory. And there's something kind of similar for C. Now, if you look at and compare that to A and B, the only difference is now these x does not have a squared. So again, to solve for y, we'd subtract x from each side, and we would take the square root. So now it's just the root of 1 minus x, and it's plus or minus also. But now the x under the radical is no longer squared. If we were to graph, that's just the a simple square rooting function. Starting at an x value of 1 and headed to the left. Again, we do have the plus and minus. The plus, I'll do in red here, that would be the upper half of this sideways opening parabolic curve. And the negative in front of that would represent the lower half of the parabolic curve. So in example 4, this is a good one. Determine the slope of the tangent line to the graph of x squared plus 4y squared equals 4 at this given point. They gave us the point. Square root of 2 is our x coordinate, and our y coordinate is negative 1 over the square root of 2. If we look at the graph, x squared plus y squared equals r squared is a circle. Plug it in a constant there, it's just going to stretch it out into an oval. So what we have here is an oval, and they're asking us to find the slope at this particular point, where this tangent line hits that oval here at square root 2, comma, negative 1 over square root 2. Again, we're going to have to do this implicitly, because if we just plugged in this x coordinate square root of 2, there is another point up here with a different slope. This would have negative slope here. So we want to plug in the x and y coordinate to make sure that we get the slope at the point that we are specifically looking for. And this equation isn't too bad. Deriving this implicitly won't be much of a chore. I'm just going to rewrite it. We have x squared plus 4y squared is equal to 4. And we take the derivative implicitly. First term, the variables do match, so that's just a 2x. Plus 4, let me back that up. We have 4y squared. Derive that with just the power rule. It would be 8y to the first times dy dx, because the variables did not match. And that's equal to the derivative of the constant is 0. So move that 2x to the other side, make it negative. We have 8y dy dx equals negative 2x now. And then we divide both sides by 8y. So we're going to divide here by 8y. And this is gone. So our derivative, dy dx, is this, which we can reduce. Factor out a 2. We're going to have negative 1x over 4y, or negative x over 4y. So there is our derivative. Come up here and write it. Dy dx, negative x over 4y. And now we want to use that to determine the slope of the tangent line at this particular point. So again, our derivative was negative x over 4y. 4y. And we want to find the slope at this point. So for the x, we're going to plug in the square root of 2. And then we're going to have 4 times negative 1 over square root of 2. And let's see here, the negatives are going to cancel out. We could sort of factor that out. That will become a positive. So our numerator is the square root of 2 divided by, and then here we would have 4 times this would be 4 over the square root of 2. And then we can turn this upper one into a fraction, and then bring up the denominator, invert, and multiply. So we'd have the square root of 2 over 1 times the square root of 2 over 4. That's here. Square root of 2 times square root of 2 is 2. Over 1 times 4 is 4. And 2/4 reduced down to a nice half. So the slope at this point on this graph is a half. And visually, just to verify that, it's a positive slope. We definitely have positive here. Just by eyeballing it kind of roughly, it's pretty darn close to 1/2. It should be. It better be, because that's an exact answer. Okay, example 5. Sort of on the same vein. Here it is. Reading the directions are huge in any math problem, especially in calculus. Here the directions say determine the slope of the tangent line at this point. They did not ask us to find the implicit derivative. They did not ask us to find the equation of that tangent line. So we can just focus in on exactly what they want us to do. Here in example 5, they're asking us to determine the slope of the graph of this at the point 3, 1. So it is very similar to example 4, but this equation is much, much harder to deal with. So let's let the fun begin and start by taking the derivative of, where's my pen? The derivative of this. And if we just, scan across this real quick here, we have a quantity to a power. This is going to be a chain rule. When we derive the inner function, there's going to be some implicit going on here because of this y. On the other side of equals, we have 100 times, and here's x times y. That'll be a product rule. So this is going to get a little involved, but then we do have a way to sort of shorten this problem up. But let's start out by taking our derivative. Left side first. The 2 comes down, multiplies by the 3. We're going to have a 6 times that same quantity, x squared plus y squared. Now 1 power lower to the first power. And then we are going to multiply that by the derivative of that inner function. So we're going to derive just what is in the parentheses with respect to x. So first term, nice and easy, that derivative is 2x. Plus then here the derivative of y squared would be 2y, and the variables don't match, so we have our little dy dx added on. Okay, that is the left side. Now that's equal to, here we'll have 100, and then we're going to do product rule. So product rule here, I'll underline in red. First times the derivative of the second is x times dy dx. Plus the second, y, times the derivative of the first. The derivative of x is just 1. And I guess we could just leave it right there. Now here's a good spot to stop and reflect on the problem. What are they asking us to do? Determine the slope of the graph of this at this point 3, 1. Did I erase? Let me come back to this one real quick. The problem we just did, example 4, when I took this derivative, and that was real easy. That was just a 2x plus 8y dy dx equals 4. You know, from here, I did solve for dy dx. I got everything else on the other side. I isolated and solved for the derivative to find this right here. If the problem said find the derivative of this, this would have been the answer. But it's not really what they were asking us for. At this point right here, as soon as we derived it and found the raw derivative, before we isolated the dy dx, we could have plugged in the point immediately. We could have taken that square root of 2, plugged it in for that x. We could have taken this, plugged it right in for that, and then started to solve this, and this would have been the only variable, so to speak, left, and we would have solved it and got the exact same answer. In this part of the problem, this is the raw derivative just as we took it. If you want to, if you're taking the AP test, you know, a problem like this could be on there, and at this point, we can plug in our x and y values right now, and we could solve for dy dx, and we can solve for the numerical value of that derivative at that point. Now, to save time, especially in the video, here's example 5 right from the book, and here's how we started out. Take the derivative of this, and what we have right now is about right here. If we continue on, the rest of this problem for a while is just algebra. We are foiling things out. We're combining like terms. We're isolating the dy dx on the left. And look how complicated this gets. They're going to multiply through here a little bit, and they got their dy dx's on the side. They combine like terms. They factor out a dy dx. You know, every little step as you're working through this is another opportunity to make a mistake, a tiny sign error, or forgetting to, you know, multiply something as you distribute. Any little tiny error is going to mess up the problem. There are maybe 100 opportunities to screw this up somewhere in this algebra. So I would encourage you, you know, if you read the directions and know what the problem is asking you, if you can, plug in that point right away, especially on the AP test. So let's do this the easy way. We're going to plug in our given point. We're going to plug in x is 3, y is 1. So 6 times the quantity. X is 3, so x squared is going to be 9, plus y is 1. 1 squared is 1. Times. Here is 2x, x is 3, so 2 times 3 is 6, plus 2 times y. Y is 1, so 2 times y is 2. And then we have dy dx. That's still our variable that we're solving for. And that is equal to 100 times, x again is 3 dy dx, plus y is equal to 1. Let's keep simplifying as much as we can. This is 6 times 9 plus 1 is 10. 6 times 10 is 60. So now we have 60 times this 6 plus 2 dy dx is equal to 100 times 3 dy dx plus 1. So that right there took some of the major parts of simplification out of the way. The algebra that we're left with now is pretty simple. We got to distribute the 60, we got to distribute the 100, collect like terms, solve for dy dx. So we distribute 360 plus 120 dy dx equals 300 dy dx plus 100. So let's see, the dy dx's, I got a 300 over here and a 120, so I'm going to subtract the 120 from both sides, and that'll make this a 180 dy dx is equal to, we'll subtract 100 here, subtract 100 here, 260. And then we divide both sides by 180. dy dx equals 180, or excuse me, 260 divided by 180. And it looks like we can simplify this down a little bit farther. Nice easy one. The zeros will just drop right off. And then we have 2 even numbers. We can at least pull a 2 out of there, and we're down to 13/9. And that is the correct answer. That is the slope at that given point. Let's take a look at the little picture that came with it. So it's sort of like a figure 8 shape or almost an infinity loop, and it goes right through the origin there. And we were looking for the slope at the point 3, 1. You know, again, above that point 3 up here, there'd be another point with a different slope. We'd have to come over and find a different y coordinate to go with it to plug in, because these implicit derivatives have both x's and y's in them when you find those. And again, if you can, you know, stop as soon as you derive, plug that point in, find that slope. Because again, the hardest part, in my opinion, of calculus is the algebra that goes with it. You know, here, the derivative was pretty easy to find. We're taking the derivative of this. We found that derivative pretty straightforward. All of this is algebra, and some of it gets very, very heavy. So, again, here, they solved down and got this was their derivative when it was all simplified, and it was solved for dy dx, turned into all this mess. And then they just plugged in the same point we did. 3, 1 went in the proper spaces. They simplified it down and got the same 13/9. A lot more work than you need to do if you understand what the question is asking you. If the question was, find the derivative of this equation, you know, here's the derivative. But they didn't ask us for this. They just wanted the slope. And we didn't need to take it to this level to find that slope.